Welcome back to this Biosystems Analysis and Modeling series. In the last module, we looked at some models that varied through time only and introduced the concepts of advection and diffusion to begin to incorporate spatial flow processes into our models. In this module, we will examine some techniques for solving these multidimensional models. Upon completing this module, you will be able to first understand how to solve multidimensional advective flow problems using the method of lines. And second, understand how to apply full grid methods to multidimensional models incorporating advection and/or diffusion. Multidimensional models are those that deal with systems that are distributed in multiple dimensions, possibly, but not necessarily, including time. For example, consider advective flow in a long, narrow tank like the one shown here. Such a system is referred to as a plug flow system because water tends to move through such a system as a plug, analogous to the red disc in the figure in the upper right-hand side of this slide. Referring to the production channel shown here, we see that most of the flow is longitudinal, moving down the channel. This is one dimension. But additionally, we may have flow in the lateral directions, vertically in the reactor channel, or side to side across the channel. However, in a plug flow situation, we would generally ignore these as being insignificant compared to the longitudinal flow down the channel. As a result, we could treat this as a system that varies in only one spatial dimension, down the channel. If our goal was to understand the time dynamics of the channel, our model would need to include an additional dimension, time. If, however, the movement in 2 or 3 dimensions was important, say for representing three-dimensional flow in an aquifer, we might need 3 spatial dimensions, and if we were concerned about the dynamics of the system, we would add a 4th dimension, time, as well. We've seen previously that adding advection and/or diffusion to our prior models resulted in the addition of a spatial dimension to our mathematics, which moves us from the realm of ordinary differential equations to partial differential equations, with each dimension represented by partial derivatives of each term that varies in one or more of these dimensions. Oftentimes, multidimensional models relevant to ecological engineering have one time and one space dimension for simulating 1D advective or diffusive flow over time. However, considering a steady-state solution to a problem distributed over a 2-dimensional area would also be an example of a multidimensional model. These types of problems are getting more difficult to solve than the ones we've dealt with in the past. As we have seen previously for ODE-based models, for simple cases, we can occasionally find closed-form analytical solutions to these models, but as soon as we add heterogeneity to the system, or consider any nonlinear processes or multiple coupled state variables, a numerical solution is typically required. As we will see, there are a couple of commonly used approaches for solving these types of models, but we emphasize that one should be familiar with both the constraints a given model imposes on finding a numerical solution, as well as the limitations of the particular solution procedure used. Unlike we saw with solving ODEs using something like scipy.integrate.odeint, PDEs generally don't have readily available solvers, and we often need to hand code a solution. So let's look at one such method that is reasonably general purpose for solving problems involving advective flow, the method of lines. The basic idea of this approach is to discretize the spatial dimension by carving it up into a series of uniform sections. We start with a continuous space as shown here. For the advective flow model shown, we would expect the concentration of C to vary continuously over the spatial dimension x. With the method of lines, this continuous space is subdivided into a series of cells, each of a width delta x. We then recast the differential terms involving partial dc dx as differences, replacing the partial dc dx with the finite difference delta c over delta x, which for small delta x values approximates the value of the partial dc dx. We then apply this modified equation to each cell in the discretized system. This eliminates one differential dimension, but because we have to apply the model to every cell, it results in a system of coupled ordinary differential equations that we will need to solve. How do we solve this resulting system of ordinary differential equations? We've covered methods for this already. Think of the SciPy ODEint function we've used before. Its sole purpose is to solve systems of ordinary differential equations. We would have to evaluate derivatives for each cell at any point in time, but those derivative equations are straightforward. As we see in the equations presented here, the concentration of C is related to the concentration in the upstream flow coming into a cell, as well as the loss from C to the flow out of the cell. Note that for the first cell, the inflow term is based on the concentration of the influent coming into the first cell. This would be considered a boundary condition. Because the model is first order in time and first order in space, we will need initial conditions as well as a single boundary condition describing what is going on at the boundary of the system. In this case, the inflow to the first cell. Solving the systems of equations for a given initial and boundary conditions will produce the time dynamics of C in the locations defined by our cells. Let's look at a more specific example modeling the flow of a contaminant P in a river. We will assume that the river is relatively fast moving compared to our diffusion rates, and our model will only consider the spatial process of advection and assume diffusion is negligible. This is a regional assumption for many river systems. Further, we will assume that flow is downriver only and will ignore any lateral or vertical flow dynamics, resulting in a model that is one-dimensional in space. In addition to advective flow, the contaminant will be subject to uptake via the biological elements in the system. The differential equation describing the dynamics of the contaminant P is shown here. Processes influencing system dynamics include advective flow and biological uptake, modeled using the Monod saturation function and assuming a fixed biological component B in the river. To solve this equation, we will apply the method of lines. The first step is to discretize the spatial dimension represented in the model. We will carve up the flow channel into discrete chunks, delta x units wide. We will consider the contaminant to be uniformly distributed in each cell, but concentrations across cells may vary. The second step is to replace any differential term partial dp dx with a corresponding finite difference term delta p over delta x, where delta p for the ith cell is the concentration gradient across that cell, meaning the difference in the concentration of the flow coming in from the upstream cell, cell I-1, and the flow leaving cell I. We apply this now ordinary differential equation to each cell in the system. If we have a total of n discrete cells, we will have n coupled ordinary differential equations to solve. The last step to consider is the application of initial and boundary conditions. Because the model is 1D in time and 1D in space, we will need an initial condition for each cell and a single boundary condition for each cell. The initial condition is straightforward. What is the concentration of P in each cell when we start a simulation? The boundary condition for advective flow problems is generally the concentration of P in the inflow to the system, so we would need to specify that for every point in time. And with our initial and boundary conditions defined, we have everything we need to solve the model. How would we do this? We've already developed techniques for this when we started looking at systems models. Runcutter method and the ODE integrators like the ODEint function in SciPy.optimize. ODEint in particular is set up to solve systems of ordinary differential equations and so provides a convenient way to apply the method of lines. The method of lines works well for one-dimensional advective flow problems, but has limitations when applied to more complex situations of processes involving higher-order differentials, for example, diffusion. We will therefore introduce a somewhat more robust approach to representing multidimensional systems that are generally termed full grid methods. The basic idea of a full grid method is to discretize all the dimensions of the problem, not just the single spatial dimension we considered with the method of lines. For two-dimensional problems, for example, time in 1D space, we can represent these models as a series of discrete points arrayed in space defined by the two dimensions. For the time in 1D space example, we would employ the grid shown here, with space arrayed along the x-axis and time arrayed along the y-axis. Each increment of time is separated by a delta t, and each increment of space is separated by a delta x, forming a regular grid. The next step in the application of a full grid method is to replace the differential terms in our model equations with appropriate finite differences. Unlike the method of lines, here we replace all differential terms, transforming our partial differential equations into algebraic relationships. We then apply these algebraic relationships to each node on the grid, introducing initial and boundary conditions as needed. A couple of questions we will want to look at more closely are, first, how do we make appropriate substitutions for our differential terms with appropriate finite differences? And second, how do we operationalize this strategy? We will look at these questions next. First, let's determine an appropriate finite difference substitution for the differential terms in our model. To do this, we will start with Taylor's theory, which, as you recall, allows us to find a value of a point given a nearby value of a point and the differentials at that point. We saw this before when we were looking at methods for solving ordinary differential equations. The basic idea is to ignore the higher order terms in Taylor's expansion on the assumption that they are small enough to ignore, then this is generally a very good assumption. If we focus for the moment at the node in the grid defined as ij, we can apply Taylor's theory to estimate first derivative values looking first to the left, where the derivative is the gradient between the ith node and the i-1 node to its left, and then to the right, where the derivative is the gradient between the ith and the i+1 node to its right. We can see that we can approximate the value of the first derivative as a difference in the concentration of the value at two adjacent nodes divided by the distance between those two nodes. We also see two slightly different forms depending on whether we are looking left or right. We also note that as delta x's get very small, approaching 0, the two forms converge to the same value, the derivative at the point ij. In fact, there are three possible finite difference replacements for our first order derivatives that we can consider. A forward difference looks to the next node to the right of the node being examined in the case of the spatial dimension depicted on the prior grids. A backward difference looks at the prior adjacent node to the left in terms of the spatial dimensions that we depicted in our prior grids. We developed each one of these in the previous slide. Additionally, we can imagine a third form that we will term a central difference that looks both to the right and to the left and divides by the distance between the right and the left nodes. In principle, any of these forms will produce the same result for very small values of delta x, but in practice, a particular form may be useful for specific situations. We will need a finite difference replacement for any second-order differentials employed in our models as well, for example, in representing diffusion processes. We start with the recognition that a second-order derivative is defined as the gradient of the first-order derivatives, capturing how fast the first-order derivative is changing. Thinking in these terms, we can approximate a second-order difference as the difference between two nearby first-order derivatives, divided by the distance between those two derivative estimates. We can then take advantage of the forward and backward differences replacements we discussed on the prior slide. Remember, these look to the right of and to the left of the node at location I in our grid. Taking the difference between these values divided by the distance between these estimates will provide an approximation for the second derivative at the location I. Because the forward and backward differences are in effect estimates halfway between the ith node and its neighbors, the distance between these two estimates is delta x. Thus, a finite difference replacement for our second order differential terms is shown here. Note that unlike first order derivative terms, where we have to choose between three options, forward, central, or backward differences, for the second order differentials, we always use the expression provided here as our finite difference replacement. Let's do a simple example where we solve the 1D diffusion equation with a full grid method. Recall that for a purely diffusive process, we can represent our concentration of a material U mathematically as du dt is equal to d, a diffusivity constant, times the second derivative of u with respect to x, our space variable, which states that the rate of change of u at any point in the biofilm is proportional to the gradient of u in space at that point. Additionally, we will assume that we have defined initial conditions and known boundary conditions for the right and the left-hand side. Let's translate this representation into our grid. Our grid will consist of two dimensions matching the two dimensions in our model space. We will portray space on the horizontal axis and time on the y-axis. We will assume time increases as we go up the grid. To develop this grid, we will first discretize or subdivide our biofilm into uniform increments of width delta x. Next, we will impose a grid of points within this space, shown here as orange nodes. These nodes extend across the width of the biofilm for the space dimension and up to represent the time dimension. Note that we place our nodes in the center of each of the subdivided spaces, since these points are good approximators of the average concentration of the substrate U in these spaces. We will refer to these as our interior nodes, and these are the nodes we will apply our finite difference equations to. Next, we will apply initial conditions. These will correspond to the nodes along the bottom of the grid, since the first row in the grid corresponds to time equals 0. Note that we need an initial condition for all points in space. Finally, we will apply our boundary conditions. Because this problem is second order in space, which we know because the spatial derivative is d2u dx squared, we will need two independent boundary conditions. For this problem, we will assume these two independent things are the concentrations of the substrate U on the left and right-hand sides of the biofilm. Note that these boundary conditions must be defined for all points in time that we want to simulate. At this point, we've completely set up our grid. The next step is to apply our finite difference equations to the grid, focusing on the interior points colored in orange on the grid shown here. To do so, we first replace all differential terms in our model with a corresponding finite difference term. In this case, we have two differential terms, du dt and d2u dx squared. For the first order term, we will use a forward difference, which allows us to estimate a future point in time based on current values. For the second order term, we use our standard finite difference substitution developed earlier. Making these substitutions results in an algebraic difference equation to replace our original differential equation. Note that at any given level of time j, if we know values of the substrate u at this level of time, we can estimate future values of u at the next time level, j plus 1. Defining lambda as d times delta t over delta x squared, and arranging the finite difference equation with unknowns on the left, corresponding to an estimate for time j plus 1, and knowns on the right, corresponding to the known values at the current time level j, we can estimate future values for the next time level above whatever our current time level is using the equation shown here. Note that information flows from the nodes below to the left and to the right to a given node at the next time level. These are the nodes that are required to estimate the substrate concentration U at the next time level. To simulate this system, we apply the resulting finite difference equations to each interior node in the first time row above the initial conditions. We can calculate the substrate value for each node in this row because these calculations are dependent on only the values from the previous row, which are known because they were the initial conditions for the substrate concentration at time equals 0. We apply our difference equation to each node in the j equals 1 row, resulting in known values for each one of these nodes. We then repeat this process for the next row, j equals 2. Again, because the values of each node in the j equals 2 row is dependent on the values in the j equals 1 row, and we just calculated all the values in the j equals 1 row, we can now solve each of the j equal 2 nodes directly. We repeat this process for each row, or time value, in our grid, successfully moving up the grid until we've solved all of our interior nodes. At that point, the simulation is complete. This is fundamentally an iterative process. For a given row, we solve the nodes in that row iteratively by applying the difference equation, and we also solve each row iteratively, allowing us to successively move up the grid. In programming terms, this is an outer loop, iterating through time, and an inner loop, iterating through space at a given point in time, applying the difference equation to each node as we go. We will need to incorporate boundary conditions into our model solution. Let's look at an example where our boundaries are defined as known concentrations of our state variable U. We will focus first on our left-hand boundary condition. Recall our finite difference version of the diffusion model, shown here. For the leftmost interior nodes at location I equals 0, the U at I minus 1 node is in fact our boundary condition. We can simply replace the U at I minus 1 value in our finite difference equation for the nodes at I equals 0 with the value of our boundary condition. For the right-hand side boundary, we can take a very similar approach, replacing the U at I plus 1 value in the difference equation with the right-hand side boundary condition. We will close this problem discussion with a discussion of the stability of the explicit solution procedure we've been reviewing here. Without going into the details, this model will be stable as long as our lambda value remains below 1/2. Values above this will cause the solution to become unstable and will yield nonsensical solutions. We see that we can improve stability by going to a smaller time step or a larger space step. However, larger space steps will decrease accuracy, and small time steps will increase computational requirements for a simulation. We will have to find a set of step sizes that achieve stability while balancing accuracy and computational requirements. Next, we will consider a finite difference representation for a system with advective, diffusive, and reactive processes occurring simultaneously. Our approach is the same as we took before. For each differential term in the model, we will replace it with an appropriate finite difference and apply the resulting algebraic equation to each interior point. The finite difference equations are slightly more complicated because of the additional process terms, but the same concept applies. Note that the reactive term R is evaluated at the node being calculated at any given point in space and time. We will still need initial and boundary conditions, and we will apply them as we did before. We can see here that this approach is quite general and can be extended with whatever processes are appropriate for the phenomenon being modeled. We also note that this explicit approach can be easily improved upon with more sophisticated mathematical techniques, but that is beyond the scope of this course, and the formulations we develop here will in fact work for our broad class of problems. To recap, in this module, we examined models that describe systems that vary in multiple dimensions, for example, time and space. Key takeaways include the following. First, to extend dynamic models to include spatial processes such as advection and/or diffusion, we can simply add these spatial processes to our model. This may involve adding a dimension to our problem and expressing the model as a partial differential equation. Second, for advective flow processes, the method of lines provides a straightforward way to solve these models. This involves discretizing the spatial dimension to transform a partial differential equation into a system of ordinary differential equations. Alternatively, for problems involving advective and/or diffusive flow, full grid methods are useful. These involve discretizing all problem dimensions, replacing differential terms with appropriate finite differences, and applying appropriate initial and boundary conditions. Finally, in all cases, we need to pay attention to step size. This affects both accuracy of the solution as well as the stability of the solution.